So this video is going through the solution of question 7 from chapter 1.7, complex numbers in book 5. So it's asking me to solve a quadratic first of all, and then express the answer in polar form. Well, don't forget, the second you see a z as your variable in a quadratic, we know that our root is most likely going to be complex, and the only way to get a solution in that case is to use the minus b formula. So first of all, I'll identify a, b and c, and then I'll fill them into the formula. And then I'll just simplify this a little bit. And at this stage, I've got a root of a negative number, so I'll have to resolve that using imaginary numbers. So I split my root of minus 4 up into the root of 4 and the root of minus 1. And of course, don't forget that's one of my key pieces of information in complex numbers is that the root of minus 1 is I. So sorting out my root 4, I get z is equal to 2 plus or minus 2i over 2. And then finally, simplifying it down, my last step, I get the roots of my complex quadratic, z equals to 1 plus 1i, z equals to 1 minus 1i. But the only issue now is that these answers are in Cartesian or rectangular form, and the question has asked me to give them in polar form. So I'll have to convert each of these separately into polar form, and then I'll be finished the question. So as always, my first step is going to be to draw a sketch. So I've drawn a quick sketch of my first one, 1 plus 1i, and now I need to draw in its modulus and its argument. So don't forget to find the modulus, which can also be called r, or z modulus as this notation says here. I'm going to square root a squared plus b squared. And in this case, that's going to give me root 2. So root 2 is the modulus of this complex number. My next step now is to find the argument, which is just the angle created between the positive sense of the real axis and the modulus. And to do that, I'm going to drop a line from the complex number to the real axis first of all. And this creates a right angle triangle. And I know 2 of the sides. In fact, I suppose really I know 3 of the sides because I'm after working out the modulus, but I'm going to work with the ones that come from the Cartesian form of the complex number. So 1 and 1, and then I'm going to use those to get tan of that angle. And I'll just give that angle a name. I'm going to call it theta. So I'll make a note that tan theta is 1 over 1, which of course is just 1. And then I'll tan inverse my 1 to figure out the size of the angle. And that's going to come out as 45 degrees. If you've chosen to do this in radians, then it'll be pi over 4. So I've found theta, which can also be called the argument of z, and that's 45 degrees. And now that I have that information, I can put the modulus and the argument together to make the complex number in polar form. Remember, polar form looks like this, or cos theta plus I sine theta. So I'll just fill in my r and my theta, and I have root 2 cos 45 plus I sine 45. Just a word on the argument in this particular part of the question. Notice that the angle that I'm looking for here is less than 90 degrees. It's in the first quadrant. And as a result, it was really straightforward to get the argument of z. Just watch out if you're in a different quadrant, there might be a little bit more work involved. We'll actually see that in the next one, 1 minus 1i. So on I go to z equals 1 minus 1i, and I've sketched my Argand diagram, and I'm going to put in my z now this time, located in this time the fourth quadrant. Take a moment to have a look at my 2 roots of my quadratic. What do you notice about them? And what do you notice about their positions on the Argand diagram? I wonder at this stage, thinking back to previous videos about anti-clockwise and clockwise rotation of angles, positive angles and negative angles, could you find a shortcut to get as far as the polar form of z equals 1 minus 1i without going through all the hoops that we had to go through over here? And at the end of the video, I'll explain to you how you might be able to do that. So again, I've marked my modulus and I've marked in my angle, and I'll calculate both of those. So modulus first. Notice how I've put brackets around each term that I'm filling in there. And that middle guy, make that really clear, that's a plus, it's always a plus in the middle. So my modulus here is root 2, And that's actually the same as it was over here in the previous part of the question. I wonder why that is. Have a think. Well, that's because you've probably already spotted that 1 minus 1i is the conjugate of 1 plus 1i. So effectively in the diagram, to get from 1 plus 1i to 1 minus 1i, I essentially reflect through the real axis. So when I reflect, I'm not moving it any further out from the origin, so the distance from the origin is still the same. Okay, next I need to find my argument, and again I'm going to begin that by just dropping a line to the real axis. Now notice that the angle that I'm looking for is not inside in the triangle that I've created, but I can find the angle in the triangle and take it from 360 to figure out the size of the argument of z. So I'll do that. Like in previous videos, I'll call this little angle alpha. So the tan of alpha is 1, and then I'll tan inverse 1 to get the size of alpha. Just watch out that alpha is not the argument of the complex number, it's just that little shaded angle inside in that triangle. To figure out the argument, I need to take that angle away from 360. And I'm going to call the argument theta as before. And I get a result of 315 degrees. So now putting the modulus and the argument together, I can write this complex number 1 minus 1i in polar form as root 2 cos 315 plus I sine 315. Now, I said earlier in the question that it might be possible for this case to actually access the polar form of 1 minus 1i a bit quicker than going through all these stages. And just before I go on to explain any further, just to point out that this answer here is a perfectly acceptable answer for polar form for z. No problem with 1 minus 1i being written in this form. But if I wanted to kind of speed up the process a little bit, and maybe if I was kind of pretty clued in to how my Argand diagram, my unit circle even operate, I could see that, okay, well, we've already noticed that 1 plus 1i and 1 minus 1i are conjugates. We've already noticed that the modulus of both of these complex numbers is equal because they're the same distance from the origin. And you've probably spotted as well that the angle in both cases is the same. And the only real difference between a complex number and its conjugate is that for the complex number in the first quadrant, I've taken an anti-clockwise rotation. And for the complex number in the fourth quadrant, I should say, I've taken a clockwise rotation. So if this angle is 45, I could consider this angle to be minus 45. And so I could have just said, okay, they're conjugates, they're going to have the same modulus, and I can simply make the angle negative. I'm not saying you have to approach the question in that way, but it is something to be aware of. And it demonstrates a fluency in complex numbers and an understanding of the relationship between complex numbers and their conjugates.